Hello everyone, welcome back to the video. In this video we are going to learn about chemical equilibrium. Now look at this reaction here, reactant to products. I'm sure it is not something that is strange to you, right? That is, given the raw materials, the reactants, they will then be converted to products. However, have you seen another type of reaction which looks like this? Do you notice in this new reaction, you still have reactant, you still have products, but what is different here is this, the arrow. Yeah, it's actually a double-sided arrow instead, like the reaction above which shows you only a single-sided arrow. Yep, so this reaction shows that reactant will be converted into products, but at the same time the products can also be converted back to the reactants. Yep, so this is what is meant by the double-sided arrow. So if the reaction goes in this direction, we call this the forward reaction because it's going forward. But if it goes backwards, meaning from products back to reactant, as straightforward as it is, we call it as the back reaction. Here I would like to use diagrams to show you what these reactions really mean. We are back to the first reaction, yeah, meaning reactants will be converted into products. So if we look at the diagrams, it looks something like this. Let's say, for example, these are the reactants. Okay, so throughout the reaction, all of them will be converted into the products, and that's the end. End of story. Simple. On the other hand, for this reaction, you can see that you start off with the reactants, but as the reaction goes on, you could also see that not all reactants are converted into products. In this state, you have a mixture of reactants and products. And look at my arrow here. What I'm trying to do is to try to demonstrate to you that at any one time, the reactant can still be converted into the products, and products can also be converted back to the reactant. In other words, these two are interchangeable. Well, the reaction will continue and it will come to a stage where the balance between the products and reactants will become a constant. At this stage, we call this as dynamic equilibrium. That means this reaction has reached an equilibrium state. But why is it the word dynamic? Because even though it has reached a constant, the products are still gonna be interchanged with the reactants, but at a balanced rate. So let's say, for example, if 4 products is converted to the reactants, at the same time you will know that 4 different other reactants will then be converted into products. This is what we call it as the dynamic equilibrium. Now we've got 2 conditions for this to take place, meaning number 1, the reaction must happen in a closed system. Everything is contained within a container, and at the same time, the surrounding temperature must also be constant. Then you can say that we have reached a dynamic equilibrium. Now I will be using this graph to demonstrate to you the changes of reactants and products when they start the reaction and after they reach equilibrium. Let's just start with reactants. See, so reactants will start off with a high concentration. So this is our reactants, decreasing because it's being used up already over time. Yeah, reactants. While at the same time, products start from 0. Okay, there are no products initially, what? So you start from 0. This is products, and it's going up because reactants are being converted to products. So these two are actually interlinked. Yeah, as reactants go down, products go up. Make sense? Because reactants are being converted to products. But as time goes by, the reactant's concentration will actually reach a constant, whereas the product's concentration has also reached a constant. So what this really means is, from this black line onwards, there is no more net consumption of reactants, whereas there is also no more net increase in product's concentration. This is dynamic equilibrium. But then again, don't forget, at this stage, reactants are still being converted to products, but the rate of reactants being converted to products is actually the same as the rate of products being converted to reactants. Therefore, the net reaction is actually zero. Now that you understand what is dynamic equilibrium all about, I'm going to introduce a new term to you known as the equilibrium constant, represented by this symbol. This is actually a value that can be calculated for every reversible reaction. So let's just look at this reaction here. A and B are the reactants, C and D are the products. Letter A, B, C, and D in red indicate the number of moles reacting within this reaction. So in order to calculate the equilibrium constant, we take the concentration of the two products at equilibrium. I repeat, we take the concentration of the products at equilibrium, multiply them. Okay, but don't forget this product C would have a power of the number of moles, and product D would have it is powered by the number of moles as well, and then is divided by the reactant's concentration powered by their number of moles respectively. So that is how we calculate the equilibrium constant. So let's try this simple calculation here. You see this reaction, okay, and given the equilibrium concentrations here, so how are we going to calculate the equilibrium constant? Recalling the formula that I've just taught you, we put in the values: product's concentration powered by the number of moles, 2 here, then divided by the concentration of the reactant. Well, because there's only 1 mole, therefore 1, and the answer is actually 0.211. It has no units, mainly because both are concentrations, therefore the units will be cancelled out. Okay, now I would like you to spend about 1 minute to actually think, what is the significance of the equilibrium constant? What if I tell you a reaction actually has a very high equilibrium constant, very high Kc, higher than more than 10? So what does this really mean actually? Did you get your answer? Okay, let's look at it logically. If you have a very high equilibrium constant, it means that this product's value must be really high as well, whereas the reactant's value must be really low, right? Okay, let us try some imaginary values. If let's say it's 10/1 versus 2/1, yeah, so you see definitely 10/1 has a higher value. So if you have a very high equilibrium constant, it means that you have very high product concentration and low reactant concentration at equilibrium. What it means is, that means the equilibrium of that particular reaction has proceeded to a very large extent towards the products. Whereas if you actually have a very low equilibrium constant, like in this case, which is lower than 1, it means that at equilibrium, only very minimal amount of nitrogen dioxide is actually formed at equilibrium. Okay, in case if you didn't understand just now, here are some diagrams to actually aid your understanding in the equilibrium constant. So let's say, for example, the star represents reactant, whereas the blue dot represents products. So you start off with this initial condition with only the reactants, and then when reaction proceeds and it reaches the equilibrium, this is what you get. You get 5 products and 1 reactant. So I would like you to think, would you classify this particular condition as a high equilibrium constant or a low equilibrium constant? Hope you got it right. The answer is actually it has a very high equilibrium constant, very high, mainly because at equilibrium you actually get high concentration of products over the reactants. In another scenario, what you see here is you start off with the same amount of reactants, but once you reach equilibrium, see what happens. You only have 2 products. The remaining ones are still your reactants. So your equilibrium constant is pretty low, mainly because you have very little products over a large number of reactants. So again, if I were to use imaginary values, no, I don't even need to use imaginary values. So in this case, the equilibrium constant would be 5 over 1. It will be 5, right? But in this case, it will be 2 over 4, and it will be 0.5. Okay, so I hope you have a better understanding on what is actually meant by the equilibrium constant. Another one more term to introduce to you, this is called the reaction quotient. Now I would like you to make this really clear, that is, reaction quotient is actually different from equilibrium constant. Although when you look at it, the calculation is actually exactly the same, but you only calculate the reaction quotient when the reaction is not at equilibrium. For the equilibrium constant, you use the products and the reactants concentration at equilibrium. But here, the products and the reactants concentration are used when they are not in equilibrium yet. So the calculation of the value of reaction quotient and the equilibrium constant actually gives you an indication of the direction of the reaction. Let's just take this for example. Say you have your equilibrium constant in blue here. So if let's say you calculated the reaction quotient and you find that the value is actually smaller than equilibrium constant, where do you think the direction will be heading towards? Will it be going to the forward reaction, or do you think it will be going to the back reaction? You got it? So if let's say the reaction quotient is actually smaller than equilibrium constant, it's pretty easy. That means your reaction quotient is here. This is not even there yet. Therefore, the reaction will actually go towards your right, meaning it will go, the forward reaction will take place. However, if you find that your calculated reaction quotient is actually larger, so that means it's here. It's larger compared to the equilibrium constant. Therefore, the reaction will now go backwards. So this is how you use the reaction quotient and equilibrium constant to predict the direction of the reaction. We shall now try this question before we end the video. So given the reaction where sulfur dioxide reacting with oxygen producing sulfur trioxide, okay, so the question says there was no sulfur trioxide present initially, meaning there are no products initially. But then at equilibrium, the concentration of oxygen given, sulfur dioxide is this, sulfur trioxide is this, and you are supposed to calculate the initial concentration of sulfur dioxide. So let us just jot down the few things that were given in the question. So here we have jotted down a few things. Now, initial concentration of sulfur dioxide is X because it's unknown. Let's say we want to also find out the initial concentration of oxygen. I call it as Y, unknown. And I also know that the initial concentration for sulfur trioxide is actually 0. It's actually mentioned here. Well, changes is something that we would like to find out, meaning throughout the reaction towards the equilibrium, what has been changed. And at equilibrium, these are the values. Okay, working with whatever we have or whatever we know. So we know that sulfur trioxide has increased by 0.036 mole per liter in order to reach the concentration value. So this has increased. Of course, we also know that if this has increased, the reactants must have decreased. But how much has it go down by? Okay, here we are going to use the mole ratio as an indication to help us. There are 2 moles of sulfur trioxide involved, and it has increased by 0.036. And since sulfur dioxide has also 2 moles, therefore we know that 0.036 of sulfur dioxide has been used up. Whereas for oxygen, there is only 1 mole, therefore it is half of sulfur dioxide, meaning 0.018 mole per liter of oxygen has been used. So if we were to calculate the initial concentration here, X will be equivalent to 0.0223 plus 0.036, giving you a value of 0.0223 plus 0.036, 0.0583 mole per liter. That's it. That's your answer. So if you would also like to find out the oxygen's initial concentration, it will then be equals to 0.015 plus 0.018. Okay, that's the end of this video. I would like you to read more about this before we move on to the next chapter, which is the Le Chatelier's principle. Thank you.